lexicographic products and wreath products. Most of this talk is going to be a bit of a historical overview of the development of these ideas, and some, I'll talk about some quite recent developments, but the most recent stuff is not my work. My contributions to this are maybe a decade or so old, but I'll get to all of that. There's going to be a fair bit of thought put into this issue around infinite graphs. I am not at all an infinite graph person, but hopefully I will be able to convey those concepts in ways that make sense nonetheless, without creating confusion. So first of all, let me say a little bit about where I came on my math journey. So I grew up in Toronto, and then I went to Trent University in Peterborough for my undergraduate degree. And then, as Shijing said, I came to Simon Fraser for graduate school. I did a postdoc in Regina, and then I moved to Lethbridge, where I've been living and working for the past 20 years. I live and work on Treaty 7 territory, the traditional land of the Blackfoot Confederacy. The Piikani and Kainai nations particularly are near this land and have cared for it for many generations. So to give an overview of my talk, I'll sort of focus on who's done work and what work they did in this area. So I'll start by talking about the contributions of Frucht and Harari, then I'll move into Sabadusi's work, Heminger's work, and then some work by Genya Han and Ted Dobson and myself. So starting with Frucht and Harari. In 1949, in the Bulletin of the AMS, Frucht looked at the automorphism groups of what he called repeated graphs. And he defined a repeated graph as just a disjoint union of k copies of a graph. So have a graph, take a bunch of copies of it, that's a repeated graph. And he looked at automorphism groups of these things. And this inspired some work by Harari in 1959 in the Duke Journal of Math. Harari introduced the idea of the composition of graphs. We'll see a number of results that came out in the Duke Journal. I think the Duke Journal may have been a little less selective at that time than it is now, but anyway. So his motivation, as he described it, for introducing the composition of graphs was, we wish to construct a binary operation on linear graphs to be called composition, such that the group of the composition of two graphs is, in general, permutationally equivalent to the composition, or the Gruppenkranz in Polya, of their groups. This problem was suggested by the work of Frucht, which I just mentioned, who gave the result for the case that the first graph in the composition is totally disconnected, so you have just a bunch of disjoint copies of a single graph. All right, so he's trying to find a graph product that produces an automorphism group that leads to the Gruppenkranz being the what happens to the automorphism groups of the graphs when you do this this particular product. So first we need to understand what the Gruppenkranz was. More modern terminology for this is the wreath product. So I'm going to use Harari's this definition. So G1 brackets G2 is the composition or Gruppenkranz of the permutation groups G1 with G2. So they're acting on the direct product of the sets that G1 and G2 act on. So G1 acts on X1, G2 acts on X2, then this composition acts on the direct product of those two sets. However, for defining the composition, what he says is it's more convenient to regard the object set X as a matrix, D1, which is the cardinality of X1, by D2, which is the cardinality of X2 matrix, elements Xij. And then what happens, what this permutation group does, this composition, or Gruppenkranz does, is we permute the rows of X in accordance with an element of the first permutation group, G1. So it acts on the rows, and then we permute the column indices in each row separately using one element of G2 for each row. So we permute the rows, and then each row gets permuted independently by potentially different elements of G2. G1 acts on the rows, G1 acts on the set of rows, and G2 acts on each of the rows individually. It can be defined for abstract groups too, but it's clearer in the context of permutation groups. And the important thing to note about this definition is that the set of rows, or each row as a set, is preserved under this operation. It might get mapped to a different row, but either the whole row gets mapped to a different row or it gets left alone. Yeah, so the degree, the size of the set that this composition is acting on, is the product of D1 and D2, and the order of this composition is N1 times N2 to the D1, where Ni is the order of the group Gi, because again, we can pick any permutation of the rows, any of the N1 possible permutations of the rows, and then independently we pick a permutation for each of the columns. We have N2 choices for each of those D1 rows. Okay, so now Harari wanted to define a graph product that had this Gruppenkranz for its automorphism group. So he defined the composition of two graphs, gamma 1 of gamma 2, is the graph gamma obtained by replacing each point of gamma 1 with a copy of gamma 2 and each edge of gamma 1 by the edges which join the corresponding copies of gamma 2. So this is the idea. I'm putting there the formal definition of what the vertices are and what the edges are, but I'm not going to actually read that. It's there for you if you want to see it, but I think a picture is much more illustrative of the concept. So the picture is, we have our two graphs, gamma 1 and gamma 2. And the first thing we do is we make a much bigger copy of gamma 1. So this is just gamma 1 blown up. So I've enlarged each of the vertices and enlarged each of the edges. And now in each of these big fat vertices, I put a copy of gamma 2. And now I replace each of these big fat blue edges by every possible edge between the corresponding copies of gamma 2. So there we go. That is the composition as Harari defined it of two graphs. If we think about, so this is now commonly referred, this product is now usually referred to as the lexicographic product of two graphs, or often it particularly when people are talking about automorphism groups, it's also referred to as the wreath product of the two graphs. You can kind of see why it's referred to as the wreath product from the picture we got. If our graphs are both cycles, then what we end up getting looks something like a wreath. And you can see that in the automorphism group of this composition, we'll certainly be able to use any automorphism of gamma 1 to permute the copies of gamma 2. So in this case, the automorphisms of gamma 1 are either reflections or rotations. We can move these copies of gamma 2 around by either rotating this big graph or reflecting it. And independently, because we have every possible edge between, say, this copy of gamma 2 and this copy of gamma 2, and we have no edges between that first copy of gamma 2, and this copy of gamma 2, say, we can do anything we like to this particular copy of gamma 2, well, any of its automorphisms, and that won't change which vertices are adjacent to which vertices. So we also get automorphisms independently. We can do any automorphism of gamma 2 to any of the copies of gamma 2. So this Gruppenkranz, yes.
Just to be clear, the red and the blue edges are both included in the graph, yes?
Yes. Yeah, I've only made them red and blue to distinguish the copies of gamma 2, but yeah, normally they would just be uncolored, all of the edges. Okay.
Thank you.
Yeah, so certainly the Gruppenkranz that Harari was talking about will be sitting inside the automorphism group of this product that he defined, the Gruppenkranz of the automorphism groups, or in modern terminology again, the automorphism group, sorry, the wreath product of the automorphism groups of our two graphs will be sitting inside the automorphism group of the composition that Harari is defined. Okay. Yeah, so the group in crowns requires rows to map to rows, if you remember what Harari said about it. And in the context of automorphisms of this composition of graphs, it requires copies of gamma 2 have to map to copies of gamma 2. If gamma 1 and gamma 2 both happen to be complete graphs, then the composition that Harari defined will also be a complete graph. And therefore, its automorphism group will not actually be the wreath product of the automorphism groups of the two graphs. So let me show an example of that. If I had taken, instead of a cycle, gamma 1, if I'd taken gamma 1 to be a complete graph, K5, and gamma 2 is still K3, then when I do this composition, I end up getting every edge between any two possible vertices in this graph. Again, the red edges are not actually distinct from the blue edges. They're all edges. I've just colored them to make it clear where my copies of gamma 2 arose. And you can see that, for example, switching these two vertices, interchanging these two vertices, is an automorphism of K15, which is the graph I have here, but it doesn't preserve these copies of gamma 2 because I've got one of the vertices from this copy moving, but the other two vertices are not moving. So the automorphism group of this graph is actually the symmetric group on 15 points, and it's strictly bigger than the wreath product of the two automorphism groups. So Harari hasn't quite done what he wanted to do, and he recognized this, but he thought that complete graphs were sort of the only problem that arose. And so he included in this paper a theorem that said the automorphism group of the composition of two graphs is permutationally equivalent to the composition of their automorphism groups if and only if not both graphs are complete. Now, it's not entirely clear to me from reading this paper if he was assuming that graphs are connected. I mean, he shouldn't have been, because the fruit example that he was working from was about one of the graphs was totally disconnected. But so he shouldn't have been assuming that, but maybe he was anyway. So he didn't leave out, for example, the empty graph. Is if both of your graphs are empty, then again, you're going to get an empty graph as the lexicographic product of your two graphs. And that's going to give you a group, the automorphism graph, rather than wreath product. So empty graphs are also counterexamples. Maybe he realized that, maybe he didn't. It's not entirely clear. But there are also other things that he definitely didn't recognize. So for example, if I take gamma 1 to be a complete bipartite graph, K33, and gamma 2 to be an empty graph on two vertices, then if I take the composition of these two graphs, I'll get the complete bipartite graph K66. So let's just see that. I start with K33, I've blown it up. I'm going to put a K2 complement inside each of those vertices. And now I replace these big fat blue edges by every possible edge between the corresponding copies, and I get a K66. And
excuse me, that's not K66.
Sorry?
It's not K66. That has K66 has six edges.
It is not K66. You're right, and but that's just because I drew it wrong. So yeah, I drew it wrong because I should have, for example, have these edges and more. Yeah, so it should be a K66, and sorry about that. I did not draw all of the edges, but it should be a K66 because I should have gotten every possible edge from the left side to the right side, right? From this vertex, I get two edges from this big fat edge, two edges from that, and 2 edges from that. So I get 6 edges coming out of every vertex. Okay, so it is K66, even though I didn't draw it right. And we can, for example, exchange these 2 vertices. That is an automorphism of K66, but it's not preserving this copy of gamma 2. And therefore it is not we did not get the wreath product that we were looking for as the automorphism group of the graphs. Okay, sorry, let me. So now moving into Sabadusi's work. Still in 1959 in the Duke Journal, so the Duke Journal clearly moved really fast in this publication. Sabadusi published a correction. So he saw that examples like the one I just showed you, he saw that Harari's work was wrong, and he introduced the term lexicographic multiplication to replace the term composition for this operation on graphs. In order to state his result, I need some terminology. So he referred to 2 vertices of a graph as being false twins if their open neighborhoods are equal. So these are non-adjacent vertices, but they have the same neighbors. And true twins if their closed neighborhoods are equal. So now these are adjacent vertices that have the same neighbors aside from each other. And a graph is almost locally finite. So now we're moving into infinite graphs if it has a finite number of vertices that have infinite valency. And in 1959, Sabadusi published his theorem in the Duke Journal that if X, your first graph, is an almost locally finite graph, and Y is actually finite, then the automorphism group of this composition or lexicographic product is the wreath product of the automorphism groups, if and only if 2 conditions hold. If your first graph has false twins, then your second graph has to have been connected. And if your first graph has 2 twins, then the complement of your second graph has to have been connected. Let me digress briefly. Sabadusi is a graph theorist from the Université de Montréal. He worked there his whole career. He is now 91 years old, so he's not doing research anymore. And he almost always used letters like X and Y for graphs, and that is because he worked at a time when graph theory was not widely respected. He worked in a department that had a lot of topologists, and he found that the topologists in his department paid a lot more attention to his talks if he called things X and Y, or like topological spaces, and if he called them G. A bit about Sabadusi. So let me show the necessity of these conditions. So suppose that this condition fails, then I'll show that we end up getting some extra automorphisms in this group. So if this condition fails, this means that X has false twins, but Y is disconnected. So here's 2 false twins in my graph X, and I've blown them up into big fat vertices because I'm going to be creating a lexicographic product. So these false twins, they're not adjacent, but they have exactly the same adjacencies as each other in the whole rest of the graph. So in each of these, I stick copies of Y, and Y is disconnected, so it has some connected components, and I suppose there are 3 connected components, but it doesn't really matter how many. I have some connected components. All right, so now we're going to find an automorphism group, an automorphism that does not preserve our copies of Y. So I'm going to take one particular connected component of Y, and I'm going to take the same connected component in the vertex corresponding to A. I'm going to take that copy, and in the vertex corresponding to B, I'm going to take the corresponding connected component of Y, so the same component, and I claim I can just interchange those. And that will be an automorphism of the graph because none of these vertices in Y, in this connected component of Y, are adjacent to anything other than other vertices in this corresponding copy of in this corresponding connected component, or they might be adjacent to something, some other blown up vertex, everything in some other blown up vertex over here. But if they are, because A and B are false twins, we have all the edges here and all possible edges here. And so we're not changing the adjacencies by switching these two connected components. All right, so this is why this condition is necessary. And let me go back and show that the other case is also necessary. So if X had true twins, then and the complement of Y were disconnected, then these are now true twins. So that means I have every possible edge between them, as well as they share exactly the same adjacencies everywhere else. These are now connected components of Y complement. So I have every possible edge between them, as well as every possible edge between these two copies. And again, I can do exactly the same thing. So every possible edge here, 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 and here, and here. And everything that was a non-edge in my other case is an edge now. And so we have exactly the same same possibility of exchanging these two connected components in the complement, because they are now all adjacent to things, to everything else in A and everything else in B. Okay, so these are necessary conditions. They're also sufficient conditions, and Sabadusi proved that in the paper. Essentially, you can come up with some nice graph theoretic constraints that show that if these conditions do not hold, then your copies of Y are blocks, have to act as blocks of the automorphism group. I don't want to get into that any further than that. In 1961, Sabadusi wasn't entirely happy with that first result he'd come up with. And so he wanted to, because it had conditions on X and Y, right? X had to be almost locally finite and Y had to be finite. So he wanted to weaken those conditions on X and Y, and he succeeded in doing that in 1961. He proved that if X is any non-empty graph, so just the only condition now is that it be non-empty, and Y has the property that any two vertices have fewer than the order of Y mutual neighbors, then exactly the same conditions hold. The automorphism group of the lexicographic product is the wreath product of the automorphism group, if and only if those two conditions hold. So this is a much better condition, and certainly this condition will be true if Y is finite, but it'll be true a lot more commonly than that. Before I continue with lexicographic products, I want to finish off sort of Sabadusi's work. And Sabadusi also introduced at about this time the idea that, you know, the lexicographic product can be nice generalized. So Harari insisted that we replace each of those vertices of X with a copy of a fixed graph Y. But why couldn't we replace every vertex of X with various different graphs? So this is what Sabadusi defined as the X join of a collection of graphs. So we start with a graph X and a collection of graphs Y sub X, one for each vertex of X. Then the X join of the Y axis is the graph you get by replacing the vertex little x of X with a copy of the graph YX that was indexed by that vertex. And then we do exactly the same thing as before. If there was a big fat edge between Y sub X and Y sub Y, then we put every possible edge between those two copies. And there's a formal definition, but again, let's go through a picture. So suppose X is that same graph, a cycle on 5 vertices. And I've got 3 different, and I've labeled the vertices now because I need to know which vertex I'm replacing with which graph. I've got 3 different graphs I'm going to use. Y0 is just going to be a single vertex. Y1 is 2 vertices, and Y2, Y3, and Y4 are all complete graphs on 3 vertices, like before. I blow up X, and I put a copy of Y0 where vertex 0 was, a copy of Y1 where vertex Y1 was, and copies of K3 where vertex 2, 3, and 4 are. And then I replace the corresponding copies by every possible edge between them. Okay, so this is the X join of graphs as Harari defined it, and that will be important shortly when we see in Heminger's work. So Heminger built off what Harari had done. And first, I'm not going to list his initial result because he got sort of the right result a couple of years after this. So let me just mention, he did have a publication in 1966 in which he got necessary and sufficient conditions. It was still in the Duke Journal. This was for all graphs now. So for any X and Y, he eliminated all of the conditions on X and Y. But he did miss a subtlety in this paper, so the theorem wasn't actually right. He published an errata in 1967, and in his errata, he had to go back to requiring an assumption on X and Y, some assumptions on X and Y. But then in 1968, he did publish necessary and sufficient conditions and some broader results in the 5th volume of JCT. That was before it split into JCT-A and JCT-B. So in order to understand his results, we need some more definitions. So suppose we have a lexicographic product of graphs, X with Y. We have an automorphism of that lexicographic product. Then he calls this automorphism natural if it does what we want it to in a lexicographic product, that is, it preserves copies of Y. Yeah, and otherwise he calls it an unnatural automorphism. Right. And then he defines a subset of vertices to be externally related in a graph if whenever you take 2 vertices in that set and any vertex outside of that set, they either are both adjacent to that other vertex or neither of them is adjacent to this other vertex. So we have a set of vertices, and if I pick any 2 vertices in here and any vertex outside, these 2 vertices are either both adjacent or neither of them is. So in other words, every vertex outside of this set either has every possible edge to vertices in this set or no edges to vertices in this. All right. So for example, if we take the vertices of any copy of Y, they are externally related in the lexicographic product. Okay. If we're going to eliminate all of those preconditions on the graphs X and Y, then we need to understand 2 other kinds of obstructions that can only arise in infinite graphs. So let's talk about those. So this is the first of these obstructions. It's called, well, Heminger called it inverting X points. So suppose that we have a lexicographic product and both of the graphs have more than one vertex. And suppose that your first graph has a vertex that's either isolated or complete. So it's either has no edges at all or is adjacent to every other vertex in the graph. Then if your second graph is isomorphic to the X join, remember that's Sabadusi's definition, the X join of a bunch of things that are isomorphic to Y, except for a copy to replace X, but every other X is going to be replaced by a copy of Y. Call X an inverting X point of gamma. Okay, so let's again look at a picture. I'm going to draw a picture this time in a few minutes. So when this happens, I'm going to explain this and then I'll draw a picture. When this happens, it turns out that there's a natural automorphism of gamma that fixes the copy of Y, well, the whatever we replaced X with inside that graph, and swaps the copy of Y that replaced V inside the copy of this graph that replaced X with the copy of Y that replaced V that is not in that copy for every other vertex. So again, this with the picture, and this is one objection to having only the natural automorphisms, because this is not going to preserve our copies of Y anymore. So here, let me draw an example. I'm going to take my graph X to be a graph on 3 vertices with a single edge. And my graph Y is going to be an infinite lexicographic product of X with itself. There are other ways to get this, but this is relatively to get examples of inverting X points, but this is a relatively simple way. So we're going to take the lexicographic product of X with Y. This is going to be isomorphic to Y, you can see, because it's just still going to be an infinite lexicographic product of copies of X with itself. But this is what it looks like. So we're going to have 3 vertices. The 3 vertices of X we blow up. And this is the vertex, sorry, this was the vertex little x, this isolated vertex. And inside this, we end up with another copy of Y. And what we're going to do is we're going to, let me change colors. Oops. So we're going to fix all of the vertices in this set, and we're going to swap all of these vertices with all of these vertices. And in order to do that and still have an automorphism, we're also going to swap all of these vertices with all of these vertices. Okay, so this will be an automorphism because you can see where the adjacencies are. The adjacencies, well, I mean, this is sort of an isolated collection in the graph, and we're swapping it with this other isolated collection in the graph, and they're isomorphic. So we can do that. This will be an automorphism of the graph, and it's not preserving this copy of Y. And therefore, it is not a natural automorphism. So this is one thing that can go wrong. All right. So now we need some more about the other things go wrong. So in 1960, Heminger different what he called a smorphism, which is a stronger sort of homomorphism. So a smorphism is a homomorphism that preserves both edges and non-edges. So it's a stronger homomorphism because it preserves non-edges. And then he had another definition, M be a partition of the vertices of gamma, such that for every A, the induced subgraph is externally related in gamma. Then we're going to define a graph to be, well, let me just say the idea. Essentially, gamma is going to be a gamma M join of a collection of graphs, and we are going to collapse each of them to a point. Yeah, so gamma M is the result of taking the quotient under a strong homomorphism where each element of the partition M maps to a vertex in the quotient. Let me switch back to blue. Okay, so here's the second obstruction. Suppose we have a proper partition of the vertices and the subgraphs induced by this partition are externally related, and we have a strong homomorphism that's onto, and there is, and we have this isomorphism. And if there is an unnatural isomorphism between this collection and this collection for some vertex, then there's an unnatural automorphism. Sorry, if there is such an unnatural isomorphism, then we will get an unnatural automorphism of our wreath product, our lexicographic product. So again, that's probably pretty confusing, but let me draw you a picture again. So of the kind of thing that can go wrong. It's a bit similar to the last example, but somewhat different as well. So this time my graph X is going to have 2 isolated vertices and a path of length 4. And y is going to be the infinite lexicographic product of paths of length 4.
Joy,
Okay,
here's one question.
Yeah.
Yeah, so is it necessary to require y is a infinite lexicographic product?
It has to be an infinite graph. There are ways that it's not necessarily an infinite lexicographic product of the same graph over and over. I don't remember, honestly, if there are other ways, ways of getting it.
Okay, thank you.
Examples of the sort.
Yeah.
But definitely y has to be an induced subgraph of itself.
Okay, got that.
A proper induced subgraph of itself.
Mm-hmm.
Okay, so when we create this infinite, the lexicographic product of x with y, we're going to get something like this. So we've blown up each of the vertices of x, and inside each of them, I put a copy of y, which looks like and what I'm going to do, actually, this time is a little bit different. So this time, the unnatural automorphism is going to swap this copy, everything in this vertex with this whole collection. So swapping those, I'm not preserving my copies of y because I've mapped sort of one copy of y to 4 separate copies of y. So I'm not preserving my copies of y. So this is an unnatural automorphism, but it is still an automorphism of the graph. This is the abstraction that Heminger missed in his paper. So Heminger's theorem then was a bit messy, but as you can see, it gives us complete, necessary, and sufficient conditions for any graphs x and y to have the automorphism group of the lexicographic product be the wreath product of the automorphism groups. The first 2 conditions are exactly the ones Sabadusi came up with. Then we have the first abstraction I mentioned that you can't have. If A is an externally related subgraph of A, then A of Y, this lexicographic product, can't have an inverting A point. And then we have to avoid the other obstruction as well, which is a little more complicated to state, that second obstruction. And he also gave a result on the automorphisms of an X join. And it's quite similar, actually. So ideally, you would like to, the big difference is that you want to be able to permute, to use automorphisms of X to permute copies of the things that you've blown up, of the vertices you've blown up. But that will only work if the corresponding vertices of X got replaced by isomorphic. You've got a lexicographic, but not so good if you've got an X join in general. So in the X join, we have an extra condition that whenever I have an automorphism of X that is trying to take the vertex to the vertex Y, then I have to have replaced those 2 vertices with isomorphic things. So if I've done that, then we get very similar conditions. So we may not have a vertex. This is most interesting if our graph wasn't vertex transitive, and then because of those vertex transitive, this is really saying that we need to take a real lexicographic product. But if it's not vertex transitive, we just have to make sure we replace
You there?
Joy, I think we lost your voice. Can you hear me?
all people talk.
You're coming back.
Yeah.
No, you're not.
Sorry, was I not?
Yeah,
Am I not hearable?
Yeah, for like 30 seconds in your last slides.
Okay, so let me just very quickly say, yeah, so this is not so interesting if this result about X
Oh,
not
You're gone again.
yeah, we cannot hear you right now.
am I gone again? Okay, I'm going to switch networks here and see if that helps.
All right.
Moment. Okay, can you hear me?
Yeah, right now it's okay.
Okay, so hopefully this will be better. So yeah, so I was just saying if X were vertex transitive, then this would really be saying we would have to have a lexicographic product anyway. But if X is not vertex transitive, then it just means that we have to replace each orbit of a particular vertex with a bunch of isomorphic graphs. All of the vertices in that orbit have to be replaced by things that are isomorphic to each other. Okay, so now moving into the work of Gania and Ted and myself, and some other mathematicians as well. So the first other thing that, or one of the other things that people have studied is color graphs. So now we are going to have colors on our edges potentially. And Ted and myself showed in 2009 that if we look at color graphs, then Hemminger's result is really still true. This statement looks a bit different, but because we're going to talk about K-twins rather than false twins and true twins. But this is sort of a generalization. If you've got a color graph that covers both cases, we call a pair of vertices K-twins if they're adjacent by an edge of color K and they have exactly the same neighbors otherwise of each color. And the K complement then is the graph you get by removing all of the edges of color K. So this covers both of those basic Sabadusi conditions are covered by one statement if we're dealing with color graphs, and then we have those other two conditions that Hemminger came up with. There's nothing really novel. Exactly the proofs that they used in their papers go through directly with color graphs. When we talk about digraphs, things get a little more interesting. Gagnon in 1980 proved that for finite digraphs, Sabadusi and Hemminger's result is still true. He says in his paper, and I have not been able to completely work this out, but he says in his paper that his results work as long as Y is finite. I think there are actually counterexamples to that. I'm not convinced that that's true, but I have not gone through in detail to figure that out. Gagnon also worked on hypergraphs. And then Ted Dobson and myself in 2009 dealt with infinite digraphs and color digraphs and showed that two additional situations can lead to unnatural automorphisms besides the ones that Hemminger found. And I don't want to get into the details of that because they get even more complicated. But some useful corollaries are that, so for example, if X is finite, and you can strengthen that, and Y is not a proper subdigraph of itself, then we get exactly Sabadusi's condition that the automorphism group of the lexicographic product is the wreath product of the automorphism groups. If and only if for every color K, if X has K twins, then the K complement of Y is connected. One very useful situation in which I think this is interesting is if the graphs are vertex transitive. So if we have the lexicographic product of two vertex transitive graphs, and it's finite, and it's not complete or empty, then it turns out that if you don't get the nice Sabadusi condition, then it's because you chose your graphs badly. So it may be the case that gamma can be written as a lexicographic product, so that the automorphism group of gamma is the wreath product of the two automorphism groups of the two graphs. Generally speaking, you won't have to change your graphs, but if you chose really badly and your two graphs were actually already themselves lexicographic products, and each of them involved either a complete graph or an empty graph, then they might combine badly, and you might have to change where you break up the lexicographic product, basically. Let me talk you know what, I'm running short on time, so I'll just skim very briefly through this. Lexicographic products and calligraphs. A calligraph is a graph whose vertices are defined by a group and the edges are defined by the connection set. So G and H form an edge if and only if HG inverse is an element of that connection set. Whether or not a calligraph is a lexicographic product is relatively easy to detect from the connection set. And there's more on this in some recent work by Ted Dobson with his PhD student, Rachel Barber, reinterpreting some work that Sabadusi did. So a calligraph is a lexicographic product if and only if you take some subgroup H of G out of the connection set S, we get a union of double cosets of that subgroup H. And this can be generalized, that we get a generalized lexicographic product if we can do something similar with, but we have potentially two separate groups, subgroups H and K, rather than just one H. And I just want to very quickly give you a picture of what a generalized lexicographic product looks like. So in the case of a cyclic group of order 27 in this case, we can get a generalized lexicographic product by taking a cyclic, a few cycles of order 9. And we have sort of two subgroups. We have sort of these big subgroups of order 9 sitting inside our group. And we also have these little subgroups of order 3 sitting inside our group. And the generalized lexicographic product, we had a lexicographic product, and these were the vertices. If we wanted to have a lexicographic product, and these were going to be the vertices of our original graph, then we would have to have every possible edge between, say, vertices there and vertices here, or no possible edges, and we don't have that. So this is not a lexicographic product with those vertices. It's not also not a lexicographic product with, say, these sets of 3 vertices, because if I take 2 of these sets that are in the same big set of size 9, we don't have every possible edge between those copies. But we have every possible edge or no edges between sets of size 3 that are in different sets of size 9. And that's what makes it a generalized lexicographic product. We have sort of bigger sets and smaller sets. And if I take any of the smaller sets inside a bigger set, then it has exactly the same adjacencies to any of the other smaller sets that isn't in that same bigger set. Okay, either all adjacent or non-adjacent. So, and there's some other recent work by Bagarian and Mermazadeh who came up with a different generalization of the lexicographic product, and they relate that to the generalized wreath product that Evdokimov and Ponomarenko defined. And I do not have time to do that. So let me just close by saying the main reference that I've been talking about is a paper by Ted Dobson and myself that appeared in the Electronic Journal of Combined Works a little over a decade ago, 2009. And so you can certainly look that up if you are interested in more information about any of this. Thank you.
Thank you so much, Joy. If you can, please unmute and clap for Joy.
Yeah. Well done. Nice talk.
Thanks.
Any questions?